Ladies and gentlemen, join me in welcoming Dino Farinacci.
Thanks, Terry. Okay, so this will be a technology demonstration. So what I thought I would do is talk about a little history of the internet and how it was designed in the late 70s, early 80s. It's been quite a long time that the internet's been around. Of course, we can't live or breathe without it these days. I'll spend about 25 minutes on that. And then I decided to have a Pecha Kucha presentation. It's a Japanese-style presentation where you shoot 20 slides, 20 seconds each. So the total, that presentation will be 6 minutes and 40 seconds exactly, okay? And I gave that presentation at the IETF last year in Berlin. Just one thing throughout the presentation, there's a color code alert. Basically, wherever you see green, we're going to be referring to concepts like identity, identifier, endpoint ID. Lisp uses a concept of an endpoint ID to address systems. And then in red, you'll see anything that's location-based. In other words, I'm connecting to the Aspen Meadows Wi-Fi or Verizon LTE or AT&T LTE. Those are where you attach to the network. Those are called locators or routing locators. And the Lisp terminology for that is called RLOCs. Okay, so let me introduce myself. Hello, my name is San Jose, California. And this is my contact card. You can reach me at this contact entry. So there's a picture of me. I'm a software engineer. My name's San Jose, California. Email address, farinacci@gmail.com. And you need a note there because it seems kind of odd that the name of the individual is called San Jose, California. But use this particular entry to send IP packets to Dino. Okay? Well, it makes absolutely no sense. Why does it make no sense? Well, my email address makes no sense also. You want to send me an email? Shouldn't you just send me email to Dino? The problem is, why do you have to know what mail provider I'm attached to? That's just an account I have. It has nothing to do with me. And why do you care if I'm attached to Outlook or Gmail or what other provider? So we're having this naming problem which has been solved quite a bit at the application level, but it hasn't been solved at the network layer. Okay? Here's another example. I have two displays here. It's my laptop. In the upper left-hand corner, you can see that this is Dino's laptop, right? You see the green circle around there saying that's my identity. That's the identifier. It's Dino. And right now, that laptop was connected to the Wi-Fi network at Pete's Coffee. Okay, that's the locator, right? That's where my packets get sent from and where I receive packets at that point in time. They travel throughout the network, makes it to Pete's Coffee Shop in San Jose, California, and that's how I get packets. It turns out that I've been assigned this address 173.11.119.245. Okay, that's fine. Is that a location or is that an ID? If I switch over to my hotspot on my phone, and it's the same computer, but now it's connected to Dino iPhone, I get this IP address 107.77.75.47. That turns out to be an IP address that AT&T is assigned on my LTE interface. Okay? Are these locators? Or are these identities? Turns out that they're both. That's the problem with the current internet architecture. We have this semantic overload. If you want to send packets to Dino and he changes locations, you have to reset your TCP connection to now send packets to Dino at some new location. We need to decouple that addressing. And that's what this Lisp does. It's a locator ID separation protocol. It's a new architecture for the internet that's been around now for 10 years that is going to allow us to do this without having to change a lot of things in the internet. It's going to be the only way we're going to be able to scale for multi-homing and mobility, IoT, and for new applications like Bitcoin applications that are going to run on the internet. So the real world doesn't operate like this, right? The real world operates on identity and location. You see me, it's Dino. I'm in Aspen, identity, location. When you go to a street corner and you ask somebody, where do you live? The you is something you care about talking to, an object, a noun, something. And live is an actual place where you can locate that person. If you say, I want to see the Mona Lisa, that's actually an identifier, and you know that the Mona Lisa is sitting at the Louvre. Well, Louvre is a location that's implied there where the Louvre is, but you can iterate this concept even further and say, well, the Louvre is an identifier which is identifying a museum that's in Paris, France. So the internet should work exactly the same way. The identity should be Dino. And of course, the location should be San Jose, California. Okay? What we want to do at the real internet layer is that we have something that translates between a human readable and understandable name called a domain name or a DNS name, and it maps to an IP address. It turns out that IP addresses has the semantic overload. This is happening at the application layer, right? When you type in www.cnn.com into your browser, that browser as an application does a translation to find out where it makes a TCP connection to. I just said where. It's not where, it's really who, right? So by changing that address that DNS maps to, you could change it to an endpoint ID and not a locator. And then what we need at the routing layer is a way to translate this EID into a locator. So maybe this endpoint ID is an IPv6 address. And maybe it maps in a mapping database to an AT&T LTE interface, maybe a Wi-Fi access point at Pete's, maybe a 5G or eNode B in the cellular network, and maybe there's geocoordinates that are associated with it. Now this looks like, if this endpoint ID has that kind of locator set, that means it's multi-homed. We know all our phones have multiple radios, so they have connections to all of them. By the way, we should use all those connections. Well, today, all the operating systems that run on these mobile phones use one or the other. How many times have you walked in to a coffee shop and you switched from LTE to Wi-Fi, but you didn't use or authenticate at their authentication portal, and you stayed on Wi-Fi, and then all of a sudden your connection didn't work? My wife says this to me all the time, and I say, turn off Wi-Fi and it'll work. She turns off Wi-Fi and it always works. Why in 2017 are humans having to do this? Worry about what network interfaces are up and down and what works. You should be able to use all of them. When I walk into Starbucks, AT&T decides I should use Wi-Fi because they want to offload the LTE network. But it turns out that there's a half a dozen people there pulling down videos, and it turns out receiving packets on Wi-Fi is much slower than receiving them on LTE. If you were on the other side running Lisp, you would know I have two locators. You could load split packets across the Starbucks Wi-Fi and the LTE interface, or just use LTE because you see that the round trip times are better. So these are the sorts of things that could happen down at the protocol stack without the users have to be involved. This is what the next generation set of protocol architectures need to do. So let's go back. Let's go back to the ARPANET and the MILNET. The ARPANET was a military research project that was funded by DARPA back in the mid-70s, late 70s. That's the picture on the left there. And it turns out that it was mostly universities and research organizations that were attached to, quote, the ARPANET. The ARPANET only had a few nodes across the U.S. They were nodes that didn't look like IP routers, but they did move IP version 4 packets. And it turns out that everybody that was connected to the ARPANET was addressed in 10/8, the IP prefix 10/8. And then the 0.0.0, those would be filled in with what IMP you were connected to and what port on the IMP you would be connected to. Of course, those systems couldn't move, right? If you moved it from one port to another port, you had to reconfigure the IP address of the system. Later, MILNET became involved, and it was 26. So now you didn't have everybody on 10. So now when the ARPANET got a packet from somebody on 10 to somebody on 26, you would have to go through these intermediate gateways, these routers that would be interconnects, as they were profoundly called. And the problem is you would need routers to know which interfaces 26 was versus 10. The problem is if you wanted to move a computer from 10 to 26, not only would you have to change its IP address, but you would have to make sure you got approval from the MILNet, right? This was very hard, but we were physically attached. Could you imagine doing that today with a cell phone or a virtual machine that's always moving around? You can't do that. We can't really do any mobility. And of course, all these systems were connected to one or the other, not multiple connections into the ARPANET, or one to ARPANET and one to MILNet. So we couldn't do any multi-homing whatsoever. Well, what if you wanted to increase the bandwidth into that system and you had a computer architecture that supported multiple NICs? You'd be able to have two interfaces, but the Internet Protocol didn't support that very well. These are the things we're trying to fix. So here's an example today. I have my cell phone. I have two radios on it, a Wi-Fi radio and a 4G radio. And it turns out today I get two IP addresses. So if we're connected to the Aspen Meadows one, there's a DHCP server that runs in the access point that gives me an IP address that's something like Dino at Pete's Wi-Fi. And since a cell phone today is only an initiator of connections, nobody can find me and they wouldn't know how to find me. If I just wanted to put an HTTP web server on my phone, people couldn't connect to it. Because, first of all, a DNS name would have to map to one of those addresses that continually changes. And as I move around, it's also going to change. Okay? Now, on the LTE network, AT&T is giving me yet another IP address. Right? This is the problem with the semantic overload. So when Dino moves, there's no session continuity. My sessions that I initiated on my cell phone will be broken. Because now if I go to the hotel's Wi-Fi network, I'm no longer Dino at Pete's Wi-Fi, I'm something else. And so what we've done is the internet architecture at the network layer should solve these problems for the applications. But what's happening now is every application is solving the mobility problem on their own. They're all sending keep alives to see who's up and who's down, when all that stuff should be done at the waist of the protocol stack. We show the protocol stack as an hourglass where it's very wide up top where all the applications live. And then it comes down into the transport and IP layer, the skinny part of the hourglass. And then it fans out to the different types of interfaces we have. You know, we have different types of radios. We have Ethernet. We have fiber channel. If you look across all types of communication. And so we need to put the keep alives and the mobility management at the skinny part so everybody in the big part can benefit from all the different types of interfaces underneath, okay? And so if we did this, we could actually put server applications on the phone. We could put the server applications on anything that moves, any entity, right? We could do hot moves with VMs. You can put HTTP servers up and keep moving them around. And as long as the IP address doesn't change, someone far away that's connected to it, keeps your connection up. This is really goodness. So what the next generation will do, will implement Lisp in a handset, for instance, and the handset will be given an IP address. So all packets that are sourced from this handset will always be sourced by this address. It never changes. And then we have a binding with an IP address, a locator that AT&T gives us, and one that Pete's gives us. And then we maintain a mapping database as part of the infrastructure that maps to where Dino is. So the applications still ask for, where is dino.farinacci.com? They always respond back with, that's who he is. And then the transport protocols always use these addresses. So any address referrals, any UDP packets, TCP packets, always use this green address. But then when you send the packet down to the network layer then asks the question, where is this EID? And then the mapping database returns these. And then what we do is we use encapsulation. We put another IP header on that packet that the cell phone originated in. And the outer header contains the locators that go through the network. And what's on the inside of the header are the EIDs. So that means the core network doesn't have to know anything about EIDs. These EIDs don't have to be based on network topology. We could run an IPv6 EID over an IPv4 only network. We could make EIDs crypto-hashed addresses. So now you can authenticate packets at any point along the way because the source address is a hash of a public key. And anybody can then look up the public key and verify the signature. Maybe we want things to be opaque in these addresses so we have privacy with our identity. So obfuscating these type of EIDs are important. I remember BMW at one point went to Verizon and said, we want all our IPv6 addresses that are on the automobile to be based on the VIN number. And Verizon said, no, well, it won't map to our topology, so we're not going to be able to aggregate and have small routing tables in the core. Therefore, we're going to have to carry host routes. Every single device would have to have an entry in a very expensive router. And this is a perfect application for Lisp because if the core didn't know about the ID and only routed on the locator address does come out of the aggregatable allocation from Verizon. So you see now how having this level of indirection in routing and addressing is going to solve a lot of problems. So you know where we're going in the future. This is no surprise. We're less tethered than ever. We're going to have so many devices that are going to have IP addresses, and we're going to always be moving around. Okay? All these devices will be multi-homed because they're going to have multiple ways of, we found out that Apple just last week said this is going to have an LTE interface, and it also has a Bluetooth interface. So it's going to go directly to the internet, and it's going to use the iPhone as a hub to send packets. It also has Wi-Fi on it as well. So why can't we use all those interfaces when it best serves us? Okay? Even more devices are going to be connected. Could you imagine connecting? I just saw a report that the number of IoT devices already exceeds the number of people on this planet. And it's going to go orders of magnitude even more. We can't store 10 billion entries in a routing table in core routers from anywhere to anywhere. This is just a non-starter. So we have to be able to have a mapping database to solve this problem. How do we do that? Well, you put the EIDs in the mapping database and you map them to locators. There's going to be a lot less attachments to the network than there's going to be devices. My body will probably have 10 EIDs, but it may only have one connection out through the cell phone. So I just did a 10-for-1 state reduction right there. So we're going to have few locators in many places, which the data plane, the packet forwarding engines have to worry about, but we'll have billions of EIDs in few places, which the control plane will worry about. And the control plane will be used in a mapping system that will be on high-powered CPUs and storage servers that's easily implementable. The mapping database is actually key because it's distributed, so it can scale. It also can be managed multi-organizationally, just like the DNS system is. The mapping database in Lisp is a pull-type database, very much like DNS. So we know that DNS scales. DNS probably has hundreds of millions of entries right now. Not all in one place, and it's key not to have it all in one place because you don't want to have replication issues or denial of service attacks, okay? So having it distributed is important, but you want it centralized for the service it provides. You want to ask a question and you want to get an answer, right? And you want it to be easy to manage. So here's an example where the database can be used to implement policy. Right now we put all our policy in routers spread all over the internet. And then wherever you want a policy, you want Dino to talk to Nancy, right? You have to put that in all the places where Dino's going to roam and where Nancy's going to roam, okay? This doesn't scale. But if Dino asked the question, where is Nancy, and the central database said, I'm sorry, you can't talk to her on weekdays, only on weekends, then I don't know her locators. Then I can't send her packets. Today, the internet defaults to sending packets anywhere. If I want to, I could DOS attack your home routers and your link going into your house very easily. I could do it so much easier today than I could do 5 years ago because now I can launch hundreds of VMs in all the cloud providers just sending pings at 500 milliseconds. That will kill your link. And now you can't watch TV or do any maybe mission critical stuff you need to do at your house with respect to your internet link. With Lisp, as long as you get a locator, that's when you can send. So you have to ask for admission control. Okay, so here's an example where Wednesday morning, the policy is Wednesday morning, where is Dino.Farinacci, and the mapping database says that the policy is weekdays. You can go ahead and provide connectivity. So what's returned back then from the mapping database is the locator set. And then I'm free, the guy that's talking to Dino.Farinacci is free to use any of those locators. But maybe the question is asked, where's Dino Farinacci? And it's asked on the weekends. And the weekend policy is, no, you can't get it. So maybe all you get back is a geo point, which means you can't send packets to it, but it's a geo coordinate. So this is just showing you, based on time of day, when you're allowed to send packets to somebody and when you're not. Okay. What if I'm sending packets to you because I'm allowed to, and now I'm sending at too high a rate, I'm starting to DOS attack you? You could tell me that you moved, and the mapping system will now return back to me a locator or maybe the State Department. So now all the packets that I was sending to you go to the State Department. State Department picks which ones you can or cannot use, right? Now, all packets that are encapsulated in Lisp are all encrypted, okay? It all uses Lisp crypto. So there's a lot of information hiding. But now we have 4 pieces of information in a packet. Who is sending to who, from where, to where. And you can do policy on all that in the mapping system. So remember this. There's going to be lots of things out there in the future. They're going to be in many places. They're going to be moving around all the time. And it is imperative that the architecture designs in up front for scale, security, and manageability. That might be tongue-in-cheek, but the world's going to get a lot more complicated. But the demands from the users is that the internet is just like plugging your power outlet into the wall. Whenever you plug your plug into the wall and you don't get electricity, you are super shocked. That should never happen. And people are feeling that way with the internet today. It must always work. And you want to be able to have movement. Our computers are no longer PCs that sit in our offices, right? They're these things that are in our pockets. We wear them. They're going to be in our clothes. And so they're going to connect the same way. So Bourne has always said the first law of computer science is that every problem is solved by yet another level of indirection. And that's what Lisp is doing. It's providing a level of indirection for routing and addressing. So I'm doing on time pretty good. So I'm going to now talk about Lisp, which is now 10 years old. Pechakucha basically is 20 slides, all graphics, and they advance at 20-second intervals. Okay, so it's a way to tell you what Lisp has done over the last 10 years in 6 minutes. Okay, now it hasn't advanced yet, so I have a little bit of time. But you're going to start laughing because you're going to find out when there's an interesting slide, I'm going to be having to rush through it. So in 2006, we had a routing workshop. The IEB had a routing workshop in the Netherlands, and we looked at the routing table growth of routing tables in core routers. And we saw that this exponential growth was happening, so we had to solve the problem. Using locator ID separation was a way to solve the problem because the host's IP addresses didn't have to be injected in the core. So we started this routing research group in the IRTF, the Internet Research Task Force, to decide how to solve this problem. And we decided using a map and encap scheme was the way to do it. Here's an example of using Lisp where the host A wants to talk to host B, but what crosses the middle cloud at time 5 is that the packets look like they're from XTRX to XTRY. And so A and B do not have to be stored in the core. And then we worked on mapping systems during this time to figure out which was the best way to ask a map server and map resolver for these sorts of things. In 2009, we became an IETF working group, Internet Engineering Task Force. And that's when we started looking at the bits and bytes, building the protocol, building implementations, building pilot networks. Still in 2009, we were working on a set of RFCs that would be experimental RFCs. Those things became RFCs officially in 2013. But this is the working group page on a lot of other use cases that we looked at back in 2009. Many things went through review for quite a long time. Then by 2010, I was working at Cisco at the time, we started building products based on Lisp. And we built them in all the operating systems that Cisco supported. And those are the various forms of functionality. An ITR and an ETR is an encapsulator and a decapsulator. An MSR and an MSMR is a map server and map resolver. We took that mapping system and then we built a pilot network in 30 countries across 500 systems. And we built it in a hierarchy based on the internet registries to make this work. And we had friends and family, Cisco customers, colleagues, researchers join this network. We did pings, all kinds of experiments to send packets back and forth. These were some of the customers that Cisco had involved, from financials to General Dynamics to Facebook, who wanted to solve an IPv6 problem, to some small state-based run networks. Wells Fargo did it for VM mobility. And then later, now in 2012, we saw Cisco supported it on not only more platforms, not only on all the OSs, but on more hardware platforms. And Cisco was putting the Lisp packet data plane functionality in ASICs and was doing it fast. Now we find other merchant silicon providers doing it for VXLAN. This is when, in 2012 timeframe, we did Lisp marketing started up. VMware started pushing overlays. John Chambers and Jim Grubb at Cisco Live 2012 demonstrated how a cell phone could roam between LTE and Wi-Fi on the stage while it was connected to a VM, and a video server was sending stuff down, sending packets down, and that VM was moving from server to server attached to 2 different data center switches. That was happening back then. 2013, the initial set of RFCs became published, and many implementations are based on this. This is the main RFC right there on one slide. There's open source implementations, there's closed source implementations, all the equipment, the sniffer vendors are supporting stuff. AVM and Furakami are German and Japanese CP per router. We have an open ListMob, which is called OOR now, has an open WRT implementation, Linux implementation. We did an interoperability test here with Arista, a load balancer from A10, Aruba, and HP. We showed that a Mac can move from Wi-Fi to Ethernet, while a VM was moving from an Arista top-of-rack switch to a load balancer. And we showed that the connection stayed up while we were doing that. We've had tons of validation over the last 10 years about overlays, and it's been validated based on VXLAN wanted to build layer 2 overlays. And it turns out that the control plane there was a SDN-based solution, but it was validation that overlays are here to stay. Then all the VC community invested a lot of money into SDWin, if you've heard of that. And that's allowing you to do overlays on a wide area network. So we see the VXLAN in the data center, and we see SDWin in access, but we really haven't seen everybody put it together. And that also supports SDN-based stuff. A lot more use cases that we started doing. This is a list of use case internet drafts in the IETF in last year in 2016, where we're doing all kinds of interesting things with security and IoT, more mobility features, very, very interesting stuff. And of course, you know, we want to apply it to the future. We know that IoT is coming. It's here. There's no way that the BGP internet as it exists today can support it. Nobody actually realizes that. There's still a lot of IPv4 and NAT devices out there, and we need to assign IPv6 addresses to all these devices. How's that all going to work? So this was the first internet draft in January 17, 2007. It was the first individual submission that became a working group later. But we're in 2017 now, so Lisp turns 10 years old. I wonder what it's going to be when it becomes an adolescent, right? And hundreds of people are responsible for contributing, from service providers to researchers to vendors. It's really been a community thing. Lisp is completely open. There's open source. There's open standards. Anybody can do it. It's one of those things that is helping the community of the internet scale to the next generation. It's all for internet goodwill. And that's pretty much it. If Anybody has any questions, I'd be glad to champion. I have about, looks like 10 minutes. Yes? The question was, is if we assign any type of address, not only the questioner said IPv6 addresses, but if, yes, you don't need to have DHCP because the EID is mostly static now. Yeah, we're saying sometimes things that are static are good, and things that you want to be dynamic are good, but you got to know which is which. So yeah, we wouldn't need DHCP or even DHCP prefix delegation in IPv6. I'm viewing that, you know, when you're born, you're given what they call a family name, and you already have a surname. Well, I think you should get an IPv6 address as you get a social security number, and that IPv6 address should be used all the time. When I address you, let's say you're John Smith, right? Your friends call you John, your colleagues call you Mr. Smith. Those are two EIDs that are used for human interaction. I think we should do this with internet as well. There's no reason why that IPv6 address can't last you the rest of your life, or you can't have multiple ones. And of course, you move around, so your locator bindings will be dynamic. Any other questions? Comments, reactions, tomatoes? So Bitcoin is quite interesting because it's, well, from my point of view, being a network layer engineer, it's just another application that moves packets. But of course, it's a very important one because it has a financial attribute to it that the other applications didn't. I remember we evolved on doing Telnet and FTP file transfer protocols in the 80s, and then we said, what's going to really move the internet is the web. And then the next generation was voice over IP. And then the next thing over it was video. Now we're going to do transactions over the internet. And then there's going to be virtual and augmented reality sort of stuff. And we need to get the internet down to 1 millisecond delays, because if I have an AR headset looking this way and turn this way and I still see that Nexus thing there, I'm going to get sick, right? And it's not going to be a very good experience. So this is what, we'll talk more about this on the panel tomorrow. But these are the sorts of things where we need the internet, the basic internet protocols to scale. And we are even looking at using blockchain to connect the map servers and map resolvers together as an alternative to some of the mapping database transport systems that we're using today. You can use distributed hash tables. You can use Cassandra databases. You can use blockchain. We have something called a DDT, which is a distributed delegated tree, which is very much organized like a DNS hierarchy is. If you have any questions or any comments or reactions, I'll be around until Saturday morning. Thanks for listening.